GCSE Physics boosters, rate of change of momentum. A little bit more about momentum now. We've got a couple of equations. We've got F equals ma, and we've got A equals delta V over t. Yeah, acceleration is change in velocity over time. Now what we're going to do is combine them and get a different equation. If we substitute for acceleration, we get F equals delta mv over t. Now delta mv, well, mv is momentum, so delta mv is change in momentum. So F equals delta mv over t. F equals change in momentum over time, or the rate of change of momentum. Rate of change, how quickly it's changing, how much it changes every second. Okay, assuming that the force is constant, then force equals rate of change of momentum. So what? Well, look at this. Would you rather, imagine you're jumping off a roof of a burning building, would you rather land on concrete or would you rather land on lots of comfy cushions? Now, personally, I would rather land on comfy cushions. Can you give me a scientific answer why? Well, using that equation, F equals delta mv over t. Now, just before you hit the floor, you've got a certain amount of momentum, and your momentum is going to change to zero rather quickly, and the floor will exert a force on you to slow you down. Now, if your momentum changes very, very quickly, then the force will be big. Okay, in other words, if little t is very, very small, then F will be very, very big. If we can make little t in that equation, t, if we can make that bigger, then F will be smaller. And this is why if you land on the comfy cushions, it takes longer to slow down. Okay, the same change in momentum, longer to slow down, so the force slowing you down is smaller and you're less likely to break every bone in your body. Now, you need to understand these examples in the context of road safety. So F equals delta mv over t. These are all examples of increasing the amount of time it takes to slow down. The first one, an airbag. If you hit an airbag, a nice big comfy airbag, then it takes a while to slow down. I mean, it certainly takes an awful lot longer than if you just hit the steering wheel. And the seat belt as well. Its job is to increase the amount of time it takes for you to slow down. This child with his bicycle safety helmet, okay, again, if his head hits the floor, without it, it will slow down very, very quickly. With it, it will increase the amount of time, so he's less likely to hurt his little head. Crash mats in gymnastics, again, comfy cushion or hard concrete. In the playground, after you've watched this video, you'll be going off to the playground, won't you? And they have like rubber floors at the playground now. And again, you're increasing the amount of time it takes to slow down for the same amount of momentum. And lastly, crumple zones on a car. The front of a car is actually designed to crumple up like a concertina, like a cardboard box. And the idea is that absorbs the energy of the collision. It increases the amount of time it takes for the car to slow down, and the driver is much less likely to get injured. So F equals delta mv over t, and all of these pictures here about road safety, etc., can be explained using this equation. I'll also mention one more thing. This is for clever students. Can you work this one out? Now, it's not a collision, but it's relevant to that equation. The pump in this jet ski ejects 80 kilograms of water every second at an exhaust velocity of 17.5 meters per second. Calculate the thrust that this produces. How are you going to do that then? I'll give you a chance to have a go. Pause the video. 3, 2, 1. The answer is, well, use that equation. Delta mv over t. How much momentum is the water given every second? So the force acting on the water is F equals delta mv over t, which is 1,400 newtons. Then from Newton's third law, that is also the force acting on the jet ski.